Hello everyone. Today we will be talking about internal combustion engine and their thermodynamic cycle and combustion of fuel inside these IC engines. Okay, and then we will be solving this assignment number 6. Uh, okay, so let's start the session. Other may join during the session. Okay, so to start with, in the last lecture. We discussed about the internal combustion engine, the different type of internal combustion engine. So one was the spark ignition engine and second was the compression ignition engine. Also the four stroke engine and two stroke engine we talked about. So to summarize, and one important thing we learned in the last session was this compression ratio. It is a very important parameter, and uh, when we will be talking about the thermodynamic cycle for IC engines, this parameter, that is compression ratio, is very important, and you will know how the efficiency of a IC engine varies with the compression ratio. So to redefine it, the compression ratio is defined as uh, the volume of the cylinder before compression divided by the volume of the cylinder after compression. So as we know from here that before compression we have this clearance volume plus this swept volume. This clearance volume is this and swept volume is from TDC to BDC, top dead center to bottom dead center. So the total volume before compression is Vc plus Vs. Vc is clearance volume and Vs is swept volume divided by the volume after compression. So after compression, the only remaining volume is the clearance volume, and the swept volume Vs is covered by the piston only. So this is this. So this comes as 1 plus Vs by Vc, and that is how we define the compression ratio. Okay. Now uh, move to the next slides. So we talked about these IC engines, the different type of IC engines, but to to discuss about the how these engine works, so what are the thermodynamic cycles, based on those cycles these engines works, we will talk about in the session. So the first thermodynamic cycle is air standard Otto cycle. So the spark ignition engines, two stroke and four stroke, both work on this thermodynamic cycle. So what is in this thermodynamic cycle is uh, this thermodynamic cycle consists of two adiabatic two reversible adiabatic processes and two reversible constant volume processes. So these constant volume processes also called as isochoric process. Okay, and yeah, so here you can see the PV and TS diagram for Otto cycle. So as we know, let's consider a four stroke engine. So in the four stroke engine, what are the four strokes? The one is the intake stroke, where the air or air fuel mixture is taken inside the cylinder. Then the second one is the compression stroke. This air or air fuel mixture is being compressed in this stroke. The third one is the power stroke, where the burning gases expand and we get the power onto the on the piston to the crankshaft. And the fourth one is the exhaust stroke. So in a four stroke engine, these four strokes happen with two revolution of the crankshaft. Okay, so these all processes can be seen on this PV diagram. So the first one is the intake stroke. So when the intake stroke starts, the piston is at the top dead center TDC, that is the point 0 here, and it is a TDC and it is a BDC. Okay, so when the piston is at TDC at point 0, when it moves down at constant pressure, the air or air fuel mixture is taken into the cylinder. At point 1, the piston reaches at BDC. After it reaches at BDC, the main compression stroke starts, and the air or air fuel mixture inside the cylinder is being compressed from point A to point 1 to point 2, from BDC to top dead center TDC at point 2. Then at point 2, when the air or air fuel mixture is, so here we are talking about Otto cycle, so here it is air plus fuel mixture. Okay, so at point 2, when the air plus fuel mixture is compressed, a spark is generated between spark plug terminals. That spark causes the burning of fuel, means the burning of fuel means the heat is supplied to the air fuel mixture. So here at from point 2 to 3, the heat Q1 is supplied. Okay, and this heat supply raises the temperature and pressure of the gas, and these burning gases further expand from point 3 to 4 in the power stroke. Okay, once the once the piston reaches bottom dead center after the expansion of burning gases, the exhaust valve opens, and from point and the pressure drops from point 4 to point 1. That process is called as blow down. Okay, and after the pressure drops to point 1, the piston moves again from bottom dead center to top dead center to exhaust the gases, to move out the exhaust gases from the exhaust manifold. So this reaches from point 1 to point 0, so again to the top dead center. So this way this whole cycle works. Okay, so this is start from 0, then 1 2 3 4, again 1 and 0, so it stops at the 0. Now now, as we see the TS diagram for the same cycle. Okay, so in the PV diagram we saw from 0 to 1 the intake stroke, and from 1 to 0 is the exhaust stroke. So when we analyze the thermodynamic cycle, we do not consider this 0 1 because it cancels out each other. So we only consider from 1 2 3 and 4. This is the real Otto cycle. Okay, so here in the TS diagram we can see from 1 2 3 and 4. So from 1 to 2 there is compression, so work is delivered to the air fuel mixture in the form of compression work WC. And then from 2 to 3, that is constant
हेलो
volume
सर।
heat addition. Anyone asking something?
सर ये कंसेप्ट ऑफ थर्मो का डिस्कशन है या अप्लाइड थर्मो का है?
Applied thermodynamics.
ओके सर, थैंक यू सर। गलत में आ गया सर, थर्मो कंसेप्ट ऑफ थर्मो में जाना है सर।
Okay, okay. You can stay here as well if you want. Okay. So here you can see from point 1 to 2, the air plus fuel mixture is being compressed. So WC work is given to the air fuel mixture from point 2 to 3, that is constant pressure heat addition. The heat Q1 is added here, and then from point 3 to 4, that is the actual power stroke, means work is delivered to the crankshaft. So WE is the output work at the crankshaft. And then from point 4 to 1, when the exhaust valve opens and exhaust gases move out from the cylinder, this is from point 4 to 1, and then that means the heat is rejected in the form of exhaust gases to the surrounding. So that is the Q2. So this is the whole Otto cycle. This consists of two adiabatic processes, that is adiabatic compression and adiabatic expansion, and two constant volume processes, that is one heat addition and one is heat rejection. And the efficiency of this cycle uh, is given by this formula, the efficiency is 1 minus 1 by RK, that is compression ratio we talked about. Okay, raised to power gamma minus 1. Okay, so here from this equation we can see the efficiency solely depends on the compression ratio. Okay, if we increase the compression ratio here, so we see if the compression ratio is increased, 1 by RK will decrease, subsequently this whole term will decrease and the efficiency will increase. Okay, so if we plot the efficiency with respect to RK compression ratio, so we can see this will vary like this. Okay, so the initially if we increase the compression ratio, the efficiency will increase highly, but as at some point or some value of RK, this increment in efficiency will be very less. So this value of RK will be around 8 to 10. Okay, and also this efficiency also depends on this value of gamma, and value of gamma for monoatomic gases is 1.67. For gases like oxygen and nitrogen it is 1.4, and for CO2 or uh, like these gases it is 1.3. Okay, so as this value of gamma increases, this efficiency also increases. Okay, so but here our main concern is the compression ratio. The efficiency varies with the compression ratio. Higher the compression ratio, higher is the efficiency. Similarly, this is air standard Otto cycle that works for spark ignition engines. Okay, SI engines. Now for diesel engines or compression ignition engines, they work on a different cycle, and that cycle is diesel cycle. So what is the difference between Otto cycle and diesel cycle is, in Otto cycle we have two reversible adiabatic processes and two reversible constant volume processes, but here we have two adiabatic processes, one constant pressure and one constant volume processor. So the main difference here is, uh, in the Otto cycle heat addition was at constant volume, but in the diesel cycle heat addition is at constant pressure. This is the main difference. So here you can see at point 23, from this point 2 to 3, the heat addition is at constant pressure uh, compared to the heat addition at constant volume in the Otto cycle. So this is the main difference here. The other things remain same, and here one more parameter, one important parameter here is the cutoff ratio. And what is the cutoff ratio? This cutoff ratio is the ratio of uh, volume at V3, the 3.3, and volume at point 2. So this is the cutoff ratio. Okay, and the efficiency of this cycle uh, comes as this. Here you can see 1 minus 1 by RK raised to power gamma minus 1. So this term is in Otto cycle as well, but the extra term here is this RC raised to power gamma minus 1 divided by gamma RC minus 1. Now as you can see, RC is the ratio of volume V3 by V2, so it will always be greater than 1. Okay, because the volume V3 will always be greater than V2. So when this value is greater than 1, you can see here the value of this parameter will always be greater than 1. When this value is always be greater than 1, then this value for diesel cycle, this whole value for the diesel cycle will be greater than the value for the Otto cycle. That means the efficiency neta will always neta of diesel cycle will always be less than cycle of Otto efficiency of Otto cycle. Okay, for the same compression ratio and value of gamma. Okay, so this is the main difference between uh, Otto cycle and diesel cycle. Now one more cycle is there, that is the dual cycle. Okay, so in the diesel engine or compression ignition engines, some engines work on this dual cycle. And what is here in the dual cycle, the heat addition in this dual cycle is both at constant volume and constant pressure. So first some amount of heat is added at constant volume, and then the remaining amount of heat is added at constant pressure. So that can be seen here. So here the heat is added Q11 at constant volume, and here heat is added Q12 at constant pressure. Okay, so it includes both the advantage in auto engine and the auto cycle and diesel cycle. And the TS diagram can be seen here. So from point 2 to 3 it is at constant volume, and from point 3 to 4 the heat is added at constant uh, pressure. Okay, so total heat added is at constant volume and constant pressure. And the efficiency of this cycle is given by this equation. Here you can see one more parameter, rp is also there. So rp is the pressure ratio, and it is defined as the rp is pressure at point 3 divided by pressure at point 2. Okay, from this point to this point. So the efficiency of dual cycle depends on pressure ratio, cutoff ratio, and compression ratio. All these three terms: Rp, Rc, and Rk. And the efficiency of the dual cycle stands between the efficiency of Otto cycle and efficiency of diesel cycle. Okay, so these are like the basics of all these three cycles. Now how the efficiency varies, and let's see the comparison of efficiencies of these three cycles. So the comparison can be made based on two things. The first is for constant compression ratio and heat rejection, and the second is uh, highest limiting pressure and temperature. So first condition is for same compression ratio and heat rejection. So here for same compression ratio we have fixed BDC and fixed TDC, between which the cylinder strokes or moves. So once we have this fixed BDC and TDC for same compression ratio, and here we can see the heat rejection for all the three cycle is same Q2. Now as we can or the piston can move in the cylinder between BDC to TDC, and the compression ratio is same. Now once you reach the point 2 in the after the compression, for Otto cycle you can move upwards without increasing the without reducing the volume. For diesel cycle you add heat from point 2 to 7. In Otto cycle you add heat from 2 to 6. Okay, and for dual cycle you add heat from 2 to 3 and 3 to 4. Okay, so now from this figure, or let's see the TS diagram here. Once we have the constant for same heat rejection value Q2, okay, the efficiency for any cycle, that is 1 minus Q2 by Q1, will depend on Q1 only, the heat addition only. And from here, from TS diagram, we can see the heat addition is maximum from point 2 to 6. That happens for the Otto cycle, okay. And then, and the minimum heat is added for the diesel cycle, and for dual cycle heat added lies between Otto cycle and diesel cycle. So we can say from here, this discussion, we can say that for same compression ratio and heat rejection values, the efficiency of Otto cycle is higher compared to the efficiency of diesel cycle, and the efficiency of dual cycle lies between both Otto cycle and diesel cycle. So here it is shown the efficiency of Otto cycle is higher than the efficiency of diesel cycle for same compression ratio and heat rejection. Now the second condition is, we can vary the compression ratio, but we limit the maximum pressure, okay. So for that condition, if we have that same maximum pressure and temperature limitation, now here you can see that in the PV diagram, first diagram, we have limited this pressure, okay. We have limited this pressure value, and also here the temperature value. So once we have limited the pressure and temperature values for all the cycles, and we allow to vary the compression ratio, right? So uh, we know that the heat addition in Otto cycle is at constant volume. So to reach this point, point 4, okay, so heat is added at points, at some this point A, okay. So for Otto cycle, we have to add heat at some point A to reach point 4, okay, to reach that pressure, because here the heat addition is at constant volume. But if we consider the diesel cycle, the heat addition is at constant pressure, so we can increase the compression ratio in such a way that we can reach the limiting pressure after the compression itself, because the addition is at constant pressure only. And for dual cycle, we have to add heat some at some point B, where the partial heat is added at constant volume, and the remaining heat is added at constant pressure, okay. So for these limitations for maximum temperature and pressure, again the heat rejected Q2 is same, and the efficiency of cycles will vary or depend on uh, heat addition. So for heat addition, let's see the TS diagram. So we can say this point 6 to 4, this shows the Otto cycle, okay, constant volume process. So we can say that heat added Q1 for Otto cycle is less than the heat added for diesel cycle, okay. So as the heat added for Otto cycle is less than heat added for diesel cycle, we can say the efficiency of Otto cycle will be less than the efficiency of diesel cycle. So for the second condition, for same maximum pressure and temperature, the efficiency of diesel cycle will be higher compared to the efficiency of Otto cycle, and for dual cycle the heat added lies between the heat added for diesel cycle and Otto cycle. So the efficiency shows this pattern for uh, the condition of same maximum pressure and temperature. Okay, so here we talked about two things in efficiency comparison. The one is for same compression ratio. For same compression ratio, the efficiency of Otto cycle is higher than the efficiency of diesel cycle, and for same maximum pressure and temperature, the efficiency of diesel cycle is higher compared to the efficiency of Otto cycle. Okay, these are the two main things, two main comparison of efficiencies. Now, now there is an interesting phenomena here, that is self ignition, that is also called as self ignition results in knocking, and fuel rating is another concept. Okay, so what is self ignition and knocking? So what happens in first let's talk about SI engine. So what happens is when we after the compression of air plus fuel mixture, a spark is generated between spark plug terminals. This spark start the ignition of the mixture. Okay, so once the ignition started, after the combustion product starts, the formation of combustion product starts, and this increases the pressure of the combustion gases, and this results in the more compression of the remaining unburned air fuel mixture. Okay, so as the combustion goes on, the pressure further increases, the piston starts moving down, and similarly the flame front, the burning gases of the flame front starts moving from the TDC to BDC. So as this flame front is moving, this is causing to this is causing the compression of the remaining unburned air fuel mixture, and at some time when the compression becomes very high, pressure and temperature of the unburned fuel plus air mixture rises to a value that is the self ignition value of the or self ignition temperature of the fuel air mixture. And if this remaining air fuel mixture that is at temperature higher than the self ignition temperature of fuel remains there for the period that is greater than the ignition lag period, then a second flame or second combustion starts from that point, from the unburned fuels. Okay, and one flame front is coming from top, and the second combustion starts from the bottom, and at some particular point these both the fronts match, though both the pressure waves matches, and a high vibration creates, that is called as knocking. Okay, and this happens after the combustion starts. uh, okay, this is the phenomena in SI engines. Now this similar phenomena happens in CI engines as well, compression ignition engines as well, but in the CI engines this happens before the combustion starts, but in SI engines it happens after the combustion starts. Okay, so we are not discussing this in details, but to brief you, this happens in the SI and CI engines, both the engines, and this causes high vibration and high vibration and sound, and cause the damage to the engine. So it is not desirable both in SI engines and CI engines. And this phenomena can be reduced if we use the proper fuels. So for that the fuel rating is there. So for SI engines fuel rating is based on octane number, and this octane number can be between 0 to 100. Okay, so 100 octane number is for isooctane and 0 is for normal heptane. And the normal petrol, the octane number of normal petrols is around 91. Similarly, for CI engines, the fuels are rated for cetane number. So normal cetane has a cetane number of 100 and alpha methyl naphthalene has a cetane number of 0. And normal diesel fuel, so octane cetane number of normal diesel fuels varies between 40 to 55. Okay, so these are some numbers. And this is knocking that is not desirable in both the engines. And for to control this knocking phenomena, the fuels are rated for their octane number and cetane number for SI and CI engine respectively. Okay, so yeah, so this is the theory we discussed. Now let's move to the assignment questions. Okay, so the first question, so before moving to the assignment question, any doubt you have, Anurag? If you have any doubt, you can ask, or we will move to the assignment questions. Okay. Okay. So the first question is the Otto cycle is a. So what is an Otto cycle? Otto cycle is a cycle for SI engines, and this is an air standard cycle, right? So air standard cycle for CI engines, no. Air standard cycle for SI engines, yes. And vapor power cycle doesn't qualify. Okay, so the Otto cycle is a air standard cycle for SI engines. So this is the right answer. Now the second question is the air. Okay. So next question is the air standard thermal efficiency for CI engine obtained through diesel engine is slightly higher than Otto cycle. Okay, so in the last few slides we have talked about in details. The efficiency varies with the compression ratio RK, but for same compression ratio RK, the value, the efficiency of diesel cycle is little lesser than the efficiency of Otto cycle, because this term is always greater than 1. Okay, so it this value of higher than 1 always reduce the, always increase the value of this parameter, the whole parameter, compared to this parameter. So the efficiency of diesel cycle is a little lesser than the efficiency of Otto cycle. So here what is here? The air standard thermal efficiency for CI engines obtained through diesel cycle is slightly higher than the Otto cycle. So no, this is not higher than the Otto cycle. Okay, for same compression ratio. But if we talk, if we talk about it in general, the practical use, the practical application, then the compression ratio for Otto engines is between 8 to 12, and for diesel engines it is from 16 to 24. Okay, so if we see the difference between these compression ratios for Otto cycle, SI engine or CI engine, then we can clearly say that the thermal efficiency of CI engine is higher compared to Otto cycle. Okay, so again here are two things. If we talk about the practical application, then the efficiency of diesel cycle is always higher than the Otto cycle, because the compression ratio is much higher compared to Otto cycles. And if we talk about for constant compression ratio, then the efficiency of Otto cycle is higher. Okay, yeah. So the next question here is, in dual cycle heat addition takes place. So we talked about dual cycle. So dual cycle, the heat addition takes place first here Q11 and then here Q12. Okay. So first at constant volume, and then constant pressure. Okay. So at constant volume, no. At constant pressure, no. So first at constant volume, then constant pressure. So the second one is the right answer. Okay. Let's move to the next question. So the next one is the self ignition or pre ignition or auto ignition is desirable for SI engine. So again, the self ignition that we call as pre ignition or auto ignition. So self ignition is desirable for CI engines, okay, but for SI engines, the self ignition leads to knocking, okay, and that is not desirable. So knocking is not desirable. Self ignition means it will lead to the knocking. So self ignition is desirable for SI engine. No, it is not. This statement is false. Okay. One minute. So this statement is false. Self ignition is not desirable for SI engines because self ignition in SI engines results in knocking, and that knocking uh, reduces the power we receive at crankshaft. Also it damages the engine. Okay, so self ignition is not desirable at all in spark ignition engines. Now the next question is compression ratio of IC engine is. So what is the compression ratio of IC engine? It is the ratio between the volumes before the start of compression and volume uh, after the completion of compression. Okay, so it is the ratio between volume before compression and after compression stroke. So that we talked about in the first or second slides. Okay, so the compression ratio is volume before compression and volume after compression. So here it is, option 1, the ratio volume of air in cylinder before compression and after compression. Okay, let's move to the next question. That is, what is the formula for compression ratio? So the formula for compression ratio is again volume of cylinder at the beginning of compression and after the compression. So again, the compression ratio RK is given by volume before compression divided by volume after compression. So volume of cylinder before compression and volume of cylinder at the end of compression. So this is the right answer. Okay. Yeah. So move to the next question. So the next question here is the diesel cycle is also known as constant volume cycle, constant pressure cycle, constant temperature cycle, or none of the mention. So let's see how a diesel cycle looks like. So here, let's see the PV diagram. So here, the heat is being added here at constant pressure, and other things remain same with compared to the Otto cycle. Okay, so the diesel cycle also known as constant pressure cycle because the heat added here is at constant pressure. Okay, so this is the right answer. And if we talk about Otto cycle, so in Otto cycle, heat Q1 added at constant volume. So Otto cycles are called as constant volume cycles. Okay. So diesel cycles are also known as constant pressure cycle, and Otto cycles are also known as constant volume cycles. Okay. Let's move to the next question. Now the next question here is, for same compression ratio and for same heat rejected, the efficiency of Otto cycle and diesel cycle. So we talked about it in details, and here we can see that the for same compression ratio, the efficiency of Otto cycle is 1 minus 1 by r k raised to power gamma minus 1, and for diesel this is 1 minus 1 upon r is power gamma minus 1, 1 by gamma rc gamma minus 1 by rc minus 1. Okay. So and we saw from this figure TS diagram that for same heat rejection here Q2, the heat added for the Otto cycle is higher compared to the heat added for diesel cycle. So that means for same compression ratio, same heat rejection, the efficiency of Otto cycle is higher compared to the efficiency of diesel cycle. So let's see the option. The Otto cycle is more efficient than diesel cycle. Yes. Diesel cycle is more efficient than Otto cycle. No. Efficiency depends on other factors. No. Efficiency depends on compression ratio, cutoff ratio, and the value of gamma only. Okay? So for same compression ratio and for same heat rejection, the efficiency of Otto cycle is always more than the efficiency of diesel cycle. Okay. Now let's move to the next question. So yeah. So the next question is, in air standard cycles, it is assumed that the real open cycle is changed to closed cycle by assuming that the combustion products exhausted to atmosphere are fed back with fresh charge in the intake system. Okay. So what this question is saying is that we consider real open cycles as closed cycle by assuming that these combustion products are fed back with fresh charge to the intake system. Okay, so all these air standard cycle, either it is Otto cycle or diesel cycle, in all these cycles the fresh air comes inside the cylinder, it is compressed, then burned, then exhausted. Okay, then a new fresh intake is taken. Okay, so all these cycles are open cycle, they are not closed cycle. But and if we even want to make them closed cycle, we cannot do that, because after the combustion, so after the combustion, this air plus fuel mixture after the combustion becomes uh, you know they goes for the permanent change in the chemical composition and all those things. So these combustion products cannot bring back to the original air plus fuel mixture in anyhow. Okay, so that's why we have to uh, we have to reject those combustion products into the atmosphere, and we only can take the fresh charge into the inlet. But for the sake of simplicity and sake of analysis, we always consider this the combustion products that are being exhausted to the atmosphere are fed back with the fresh charge in the entire system. So yes, we assume that the uh, this combustion products which are being exhausted to the atmosphere are back into the cylinder, into the engine, in form of fresh charge. Okay, so that is true. Okay, so these are the question from assignment 6 from 2021 assignments. And if you have any doubt you can ask. So here is Anurag Bala. If you have any doubt, you can ask. Or if you don't have any doubt, we can close the session. Okay. Okay. So it seems that no one has any doubt. So we are closing the session here. Okay.